All right, so there's 3 types of natural selection, or 3 shifts in natural selection. Always your dotted line or something is going to be the original population. In this case, it's the dotted line. And normally, actually, I'm going to ask you a higher thinking question. Why do you think the original population is a perfect bell-shaped curve? I'm going to pause so you could think about that. Abby, what has to exist for evolution to occur, and why do we start with a bell-shaped curve? Genetic variation within a population, and a bell-shaped curve shows genetic variation. There's a little bit of everybody, right? Now, if directional selection occurs, what's happening?
The population, the tree.
I'm going from a bell-shaped curve to directional. What's happening? One extreme survives. One variation within that population is favorable and survives and reproduces and evolves. Yes? If I'm in disruptive, and directional can be either direction, by the way. Right extreme or left extreme, yes? Okay. Disruptive, let's highlight the U. That's not really a highlighter. And let's highlight the U-shaped curve, because that's what disruptive is, yes? Right? Uh-huh. What's happening here?
Two extremes.
Good. 2 extremes survive, or 2 of that favorable trait can reproduce and evolve. What about stabilizing? Instead of the extremes? Average. Good job. The average trait is favored in a specific scenario, and the population with the average trait survives and reproduces offspring. So, describe using this diagram, describe what may have led to directional selection, or which of those in the diagram is directional selection, and what may have led to that to take place.
That one.
So you're pointing to this one, or this one?
The bottom left.
Okay, so this is directional selection. I know because I have a perfect bell-shaped curve for my original population, and over time, so I know it, because some people might have been looking at it this way, but this is happening this way, and I know this because I have a perfect bell-shaped curve, and then there's a slight shift, and then all of a sudden there's a shift in one direction where one extreme survives. What happened? Who could tell me? Let's talk first about what's the variation of the original population.
Light beetles and dark beetles.
Color. We've got a variation of color. Daniel.
Something happened that...
I need to know what does something happen. Yes.
Let's say like the environment, like the trees got burned and there's more black soot on the ground.
Okay.
So now the beetles are protected from predators.
So the beetle's trait is to be able to camouflage within their environment so predators don't target them as much. That's a great, wow, that was a good explanation. So there was an external condition like a fire, there's a lot of soot in the ground, and the beetles that are dark can hide within that, and the beetles that are light become easy targets, hence the favorable trait being dark, okay? You're gonna have to do that for each scenario. So this we know is directional. What's the middle one?
Stabilizing.
What, stabilizing, what's the other one?
Disruptive.
And you might get one or the other, or any type of evolution, and have to give always an environmental condition and talk about the variable traits and the favorable trait, and which trait is able to survive, causing the population for that specific species to evolve. Okay?
What would you say for stabilizing?
Who could give me a stabilizing? Or who, let's do this better. I'm going to pause and then I'll ask. All right, more evolution. This is a perfect example of a symbiotic relationship, because we know this, right? Birds feed off flowers, or bees feed off flowers, and then they spread the pollen. What type of evolution is this? Where 2 species have evolved over a long period of time to live closely together. Nobody's ever heard of this? I'll give you one letter. Yes. And it's associated with mutualism and predation, obviously, because organisms co-evolve to live closely together. Evolution by artificial selection. What's another word for that? What's a popular, what? Selective breeding. What's another word for that? Genetically modified organisms, or GMOs. Big topic in environmental science, right? Don't only think of, obviously we selectively bred in originally animals, right? Out of opportunity for profit, but we selectively breed crops all the time. Not only for fast growing, survive environmental conditions, but also for opportunity to sell, right? Because that's what it's all about. And then we have evolution of resistance, which is what? Anybody? Yes? Poison is a good word. So you want to know that some organisms can tolerate chemicals that are designed to kill because they carry a favorable trait. And in this case, if you're looking at this picture, this is my original population. Where are we? Here. Or here, yeah. And then we had some spraying, and this is what happened. What type of, that's kind of hard to tell, but this is a form of directional selection, except we don't have a serious variation within the original population, but only really one is surviving, yeah? So they're kind of intertwined. Not the best example here because we don't have a perfect variation. But examples are going to be pests and bacteria. This is a perfect example of evolution happening today because of pesticides and antibiotics. So for example, how many of you have had to take antibiotics in your life? Some people have never taken antibiotics in their life. Mm-hmm. And then how many of you, after you took antibiotics, the doctor sent you a new one? Yeah? How many of you took antibiotics and didn't take it for the 10 days, even though they said to take it for 10? You took it 3 days and you're like, I'm good. You led to evolution of that bacteria, right? So you expose them to a chemical, but you let them reproduce with a little bit of that chemical, hence creating a new population that might develop some kind of tolerance to that chemical. So now when you needed the antibiotic, it didn't work. That's why they had to send you a new one. Yeah. So, yeah.